All right, class, we're going to learn about Kirchhoff's law, how to calculate the different parts of the circuit: resistance, current, and voltage. As long as you have two of those three, you can figure out what that third one is. All right, so conductors and insulators. Identify conductors and insulators. Anything that does not conduct electricity is going to be the highest resistance. You're not going to want to have a insulator that allows any amount of conductive properties whatsoever. Otherwise, if you're working on electricity, that can be very dangerous. All right, so conductors would be the ends of the pliers, the wires. The insulators would be the insulation that's on the outside of the wires and the individual wires themselves that are insulated from each other, and the handles of the pliers. All right, electrical current circuit is a system of conductors and components forming a complete path for current to travel. All right, so you've got voltage, is the symbol is V. Current is amps, which is A amps. Resistance is ohms, which is the horseshoe symbol there. All right, resistance in a circuit. Resistor are components that create resistance. So if you put a resistor on the in a line with the components, it is going to allow less voltage or less current to travel through the light bulb. Measuring voltage. All right, first thing you're going to do is with your multimeter is, if you can see where the dial is dialed into 20 volts DC. Any voltage given off by a battery is direct current. Anything given off by, say, your outlet or a anything plugged into an outlet. I'm not sure where my mind went, but anything plugged into an outlet is going to be operating on alternating current. All right, so you got your multimeter set up correctly, and measure across the component. You're going to put the negative and positive on each of the different poles to the battery, and with the switch, the red is going to encounter the positive first, and the black is going to encounter the other side of the component. Same with the resistor. Your red is going to be lead, and your black is going to be on the other side of the component. And same with your light. So your red is always going to be lined up on the side that the current is traveling. All right, multimeter. Different types. They're all pretty expensive. Voltage is volts, current is amps, and resistance is ohms. Just got to remember, current is measured in amps. That's the most difficult for some reason to remember. Measuring current. All right, so measuring current, you have to connect the multimeter so that the current is flowing through the multimeter. So first thing you're going to do is you're going to find 20 milliamps DC, and you're going to, it's got to go through the meter, so you're going to disconnect one of the wires. In this case, it's right between the resistor and the switch. And red comes first because it's in the direction of the flow of the current, and you want it to keep on continually going through the multimeter in the same direction that it's going through the circuit. All right, measuring resistance. First thing you do is you're going to remove power, and you're going to dial in, I think it's is it 20 volts? I'm sorry, ohms. 20k ohms. Anything else would be way over, and anything else would be way under. You want something that's close to what you got. Measure cross component being tested. So power must be off, so you take the battery out. And it doesn't matter when you're checking for resistance. Remember, it does not matter. The current's not flowing. You're just checking for resistance. So it doesn't matter if red or black is on left or right. Either way, you're going to still get the same reading. And then you just go across the components to figure out what is the resistance of that component. And then you can figure out what is the voltage drop across that component and how much voltage it would take to get through all these components and still provide enough voltage to power up all the components. Alright, so this is why current is kind of hard to memorize. If you look at current, the abbreviation is I, units is amps, and symbol is A. All the other ones are pretty much straightforward logic. Current is just one of those ones that you have to kind of memorize. The abbreviation and the symbol are something that you just have to remember. Units is in amps. Okay. All right, voltage equals current times resistance. Current equals voltage divided by resistance, and resistance equals voltage divided by current. So you can go with the disk or the pyramid. This is your way that you can find the variable. If you are going to solve for V, which is voltage, you're going to put your thumb over V, and it's going to be I times R. Solve for I, put your thumb over the I, and it's going to be voltage divided by resistance. If you're going to solve for resistance, you put your thumb over the R, and it's V divided by I. Alright, so in this example we have 6-volt battery. The light bulb is a 150 ohm resistor, so it's going to be to solve for current, you're going to divide voltage by resistance, which is going to be 6 divided by 150. There it is. You put your thumb over the I, and 6 divided by 150 is 0.04 amps or 40 milliamps. Milli, to convert amps to milliamps, you just multiply amps times 1,000, which gives you 40 milliamps. And you can see the difference on the left and right. Left being the series circuit and right being the parallel. With parallel, both ends of the components are connected together. Multiple paths for current to flow. Series, only one current for it to flow. Kirchhoff's voltage law, KVL. The sum of all voltage drops in a series circuit equals the total applied voltage. Kirchhoff's current law, KCL. Total current of a parallel circuit equals the sum of the individual branch currents. Alright, so series circuit. Take out one bulb and they all go out. Alright, so this one is straightforward. We've got we get into the parallel circuits, that's when it gets kind of complicated, but resistance total is just R1 plus R2 plus R3. Voltage, let's go back. Voltage is V1 plus V2 plus V, and the number of voltage drops. Alright, series circuit, the current flowing through each component. Let's back up. The series circuit uses the laws of circuit theory to calculate the following: total resistance, current flowing through each component, the voltage across each component. All right. Yeah, that's the same one. Yeah. All right. Resistance total is R1 plus R2 plus R3. So it's going to be 1.2 k ohms is going to be 1,200 ohms. So 1200 plus 470 plus 220 is 1900 or 1.9 k ohms. To convert ohms to k ohms, you would divide 1900 by 1000, and that would just basically move your decimal point 3 points to the left. Total current through each component is current total equals volt total divided by resistance total. Resistance total is 1.9 k ohms divided into 12, which is 6.3 milliamps. All right. So if you divide, 6.3 milliamps. Okay, we'll just leave it at 6.3 milliamps. All right. Okay. Since this is a series circuit, 6.3 milliamps. All right. Okay. So voltage across this component. Voltage 1 equals current 1 times resistance 1. Ohm's law. 6.349 was, 1 second. I'll go back a slide. I want to see, okay. Just backing up here a little bit. All right. Voltage across each component. 6.349 milliamps times 220 ohms. 1.4 volts. Voltage 2 equals current 2 equals 6.349 milliamps divided by 470 ohms equals 2.984 volts. And the current is basically in a series circuit, the current is going to be the same across each component. So 6.349 times 1.2 k ohms equals 7.619 volts. All right. Okay, to verify voltage current law, 1.397 plus 2.984 plus 7.619 should all add up to be 12 volts. So you calculate the voltage drops, and all those voltage drops should equal the total voltage that you put into the circuit. Okay, 12 volts equals 12 volts. All right, parallel circuit, a circuit that contains more than one path for current to flow. All right, take out one, the other ones work. All right, so this is where it gets a little complicated. Total resistance, RT, is equal to the reciprocal of the sum of the reciprocal. So you're going to have to memorize this one. So you have 470 ohms, 2.2 k ohms, 3.3 k ohms, and they did not convert it all to ohms. They just kept it as is, and so the voltage across this component, voltage 1, 2, and 3, we're going to use this circuit theory to calculate the following. The current across the 3 resistors, and use the results to verify Kirchhoff's current law. All right, total resistance equals 470 is your first resistor, 2.2 k ohms is your second, 3.3 k ohms is your third, and when you put that into your calculator, you're going to get, make sure you set up your parentheses correctly for the bottom values, and you should come up with 346.59, what they rounded up to 350 ohms. Voltage across each component is voltage 1, 2, and 3 equals 15 volts. Back up. Okay. Current through each component is going to be current equals V1 divided by R1. 15 divided by 470 is 31.915 milliamps, or 32 milliamps. All right, let me look at the calculator real quick. I want to verify something. Let's see. Oh, okay, yeah. 15 divided by 470 is 0.0319, or amps, 0.0319 amps, or 31.915 milliamps. Okay, that's what they did. All right, so current on 2 is going to be 15 divided by 2.2. 15 divided by 2.2. Yep, 6.818 milliamps. Current on 3 is 15 divided by 3.3, which is 4.545 milliamps. And current total equals voltage total, which is 15 volts, divided by resistance total, which was 346.59 from the previous slide, which equals 43.278 milliamps, or 43 milliamps, rounded down to 43 milliamps. All right. Verify Kirchhoff's current law. I1 plus I2 plus I3 equals I total. Let's see, 31 plus 6.8 plus 5, 4.5. 43 equals 43. Okay. Contain both series and parallel arrangements. What would happen if you remove light 1? Just a quick quiz. Light 2 and 3 would go out. All right. Electrical power. Electrical power is directly related to the amount. This is just the last thing we got to learn here. Power is directly related to the amount of current and voltage within a system. Power is measured in watts. A current place that wattage is used would be in cycling. They want to know how many watts their output is to figure out what their power level is compared to the other bike rider. And power is current times voltage. All right, so that's it for that. We're going to take that knowledge into actually building our circuits in Tinkercad, and we're going to learn about visually see what happens when we don't put enough resistance into a circuit, and mix in a little Arduino and a little bit of robotics, and have some fun. All right, see you guys in the next lesson.